Hello everyone. This will be our feasibility study on our project titled as Field Robot with Autonomous Navigation. I'm Bimalka and I will be delivering a brief introduction about our project. Our problem definition is developing a generic field robot with autonomous navigation, which can operate in an area constrained, non-dynamic outdoor environment. Basically, let's say in our university premises. Our project has three main objectives. One is modeling a generic field robot platform suitable for research purposes. Here we are not targeting any specific application. We are just building a platform which is suitable for research purposes. The next one is experimental and optimal fusion of light detection and ranging, camera, inertial measurement unit, and real-time kinematic sensors. The next objective is demonstrating autonomous navigation in physical environment. This will be, in this case, it will be our university premises. When it comes to the project scope, this is the platform that we received from our senior batch. They have used it for precision agricultural based application. We will be less focusing on the mechanical design improvement. We will focus more on sensor fusion and the robot operating system based software stack. The robot is fully autonomous. The robot has fully autonomous navigation capabilities, and it also has remote manual override function. The top layer of the motion controlling unit, the mission planning relies on pre-built map that we will be building through a pilot run before deploying the robot into the actual field. When talking about the limitations of the robot is battery powered, therefore the amount of weight it can carry and the maximum speed that it can move will be limited. As of now, we can say the motion speed will be similar to the normal walking speed of a person. And the robot is intended to operate in a semi-structured outdoor environment, such as farms, airports, parks, hotels, likewise. And we plan to build the system to operate in sunny weather. We do not plan to deploy it in night time. And in addition to that, the robot cannot perform in public roads. It means it cannot identify traffic lights, traffic signs, or it will not be able to navigate through urban road. When it comes to the potential applications, there are several applications areas such as precision agriculture, autonomous lawn mowers, autonomous security robots, autonomous carts, golf buggies, resort transportation. And in addition to that, our main focus is building a research platform to test models and algorithms used in autonomous field robots. The pictures that I have put in the slide were not randomly taken from internet. They are products from commercially available manufacturers. The literature review will be presented by Ravindu. Over to you.
Thank you. Regarding literature review, we are doing the literature review in many areas as sensor fusion, object detection, and tracking, navigation, and navigation systems. First, when we talk about sensor fusion, out of the literature survey we done for the sensors and the sensor fusion, we obtained many sensor types such as camera, radar, 3D LiDAR, 2D LiDAR, and then we obtained how do we fuse these, and out of them we focused on LiDAR, visual, and IMU fusion. Here, camera gave the best field of view and it works well under darkness. And the 3D LiDAR has a limited field of view, but it has a great range. Therefore, to get the maximum field of view, range, velocity resolution, and to work it well under light disturbance, we fuse LiDAR, visual, and IMU to obtain the output. Next, talking about the object detection and tracking. There are three methods for 3D object detection as monocular camera based, point cloud based, and fusion based. As I mentioned before in the previous slide, we selected the fusion based method. Therefore, under fusion based method, there are several methods for object detection such as mentioned in this slide. Out of them, all can detect vehicles, but only thrust and point pillars, point painting and AVOD techniques can detect pedestrians and cyclists. Even though higher frame rate is preferred, since our robot is moving at walking speeds, we don't need the high frames. But all of this data is tested on KITTI test dataset, and depending on our requirements such as detecting vehicles, cyclists, and pedestrians, and since a higher frame rate is preferred, we object detection. And in the navigation system, we divided the navigation system into localization, path planning, and mapping. In localization, we found three different methods for localizing as GPS, RTK, and LiDAR vision-based GPS. Here, the GPS accuracy, we get up to a meter level, and RTK, we can get up to a centimeter level. Here, depending on the availability of the previous RTK and the cost and coverage, we selected RTK for localization of our robot. When going to the mapping, there are several mapping techniques as 2D map, 2.5D, 3D point cloud, Octomap, and SegMap. 2D map gives the worst accuracy and the worst wealth of information, but due to its lowest memory and hardware requirement, it performs well. In the SegMap, it gave the best accuracy since it detects and segmented the objects throughout the map, and also it has the most wealth of information, but its computation complexity is very high. Depending on those both two positive and negative features, we selected the 3D point cloud map because we already have a LiDAR and we can use RTK for localization while mapping using the LiDAR. Next, in our literature survey, we did the path planning. Here, we did the path planning for global and local path planning. Out of them, A-star and D-star algorithms are discussed for global path planning, and depending on the accuracy and the amount of grid pixel search, we selected D-star for global path planning. And in local path planning, we selected the DWA techniques because it gave the best accuracy and best object avoidance for our local path planning. Over to you.
Okay, thank you. Hello everyone. I'm Geeth. I'm going to be talking about methodology of our robot design. Next, please. When it comes to the methodology of our sensor, the robot is about optimal fusion of LiDAR, camera, IMU sensor, and RTK. In LiDAR, we get 3D point cloud of the surrounding of the robot. In a camera, we get RGB frame, and from IMU sensors, we get the orientation of the robot. From RTK, we get accurate GPS positions. Additionally, we have a graphical user interface for the user to control the robot, which the user can give the location of the robot to move, and also some important information about the robot will also be there. And also manual override remote controller will be also added to the robot, which we can override the robot to control manually. In testing and manual controls, we are using these features. Next, please. When it comes to system architecture, we have two controls, as you can see in slides. One of them is to do the complex computational tasks. So for the high-level controller, we have used Jetson Nano Developer Kit. in that, we have used the LiDAR and image processing tasks have been computed in there, and also the RTK unit, IMU, manual override unit, and mission planner GUI also have been connected to the. And in the low level controller, we have only focused on the motor driving part, and also the LCD display on robot buttons and ultrasonic sensor also have been connected to the secondary controller. For secondary control, we have used Arduino Mega controller. In the robot driving functions, we have connected high power DC motor drivers. So those drivers will control two motors in differential drive. Over to you, Vithu.
Thank you, Geeth. And talking about the approaches, we mainly came up with two approaches of the technologies and the methods we chose. The first approach is to use an RTK GPS based localization with LVI fusion. LVI stands for LiDAR camera and IMU fusion, and LVI fusion based on local object detection, tracking, and free space detection. For planning, we plan to use local LVI fusion data based on behavioral planning. And for controlling, for both approaches, we plan on using steering control and speed control based locomotion controlling. And for 3D object detection, we came up with three methods: frustum point pillar, point painting architecture, and aggregate view object detection. And we intend to use frustum point pillars. As the second approach, we plan to use SLAM algorithms for localization and mapping, and use it to a wide range so that we do not depend on the RTK. And we also plan to use a 2D or a 3D map and use it for navigation and object detection and avoidance as the planning mechanism. And as I said before, for controlling, we plan to use the steering control and speed control based locomotion controlling. And for 3D object detection and mapping, we are planning to use integrated SLAM algorithm. And due to the computational limitations and in the implementation, we plan on starting with the approach 1. And speaking about the financial aspects, we have many resources required. Some of the resources are currently available for us at the UAV lab. For example, the robo platform, the RTK unit, the 3D LiDAR, which we are going to use, is Velodyne DLP16. Raspberry Pi cameras, motor drivers, and the battery pack are currently available at the UAV lab, and we have tested it for the working. Which are not available are Jetson Nano Development Kit, Arduino Mega, IMU GSM module, and 2.4 GHz NRF module for testing purposes. We have already planned and imported the Jetson Nano Development Kit. Speaking about the risk analysis, shipping delay of the Jetson Nano is a big risk for us, and if it is delayed, it can delay the whole timeline of our project. And unavailability or high cost of the reliable hardware components due to the country's economic situation, and the support duration of the hardware and software we are going to use. And since it is an year-long or 10 months project, the support duration may affect our project as well. Speaking about the technical risks, the probability of malfunctioning of the current robo platform and components, complexity of space-time alignment of multi-source data frames, disruption of GPS satellites and service for a longer duration in which the robo may not be able to localize itself, and the disconnection between the base station and rover in RTK, which affect the localization of our robo. So these are the technical risks that we are hoping that will delay our project. And speaking about the budget, the main cost of our budget is the Jetson Nano Development Kit that amounts to $299. And since we are importing it from abroad due to the unavailability of the board in Sri Lanka, we have made all the other price in USD as well, and the total cost is less than $450. Speaking about the task delegation, the feasibility study, robot design, the integration system and demonstration will be done by all four of us, and the main other aspects such as RTK implementation and sensor fusion, mapping, navigation, object detection will be divided among us. Geeth and Ravindu will be looking after RTK implementation. Sensor fusion will be done by Bimalka and Ravindu. Mapping will be done by Bimalka and Ravindu. Navigation and localization by Geeth and myself, and object detection by Geeth and myself, and also electronic assembly by Bimalka, Geeth, and myself. Speaking about the timeline, currently now we are at our feasibility presentation and preliminary testing stage of the robo platform. By December, we plan to develop the robo platform and test the sensor and RTK integration. By January, we plan to integrate the LiDAR camera and start the sensor fusion. By February, we plan on optimizing the fusion, and by March, we plan on working on the map building and path planning and object detection optimization. By April, we plan to test the map building procedure and obstacle avoidance optimization and electronic assembly. By May, final testing, and June, final demonstration and presentation of our project. And these are the references that we used to do the literature review for our presentation. Thank you.